In this video, we're going to continue our discussion of multiple degree of freedom systems. And here we're going to discuss coupling of equations of motion. So we will again consider the simple 2 degree of freedom system as shown here. Its equations of motions were found to be mx1 double dot plus kcx1 minus kcx2 is equal to 0, and mx2 double dot minus kcx1 plus k plus kcx2 is equal to 0. These equations are coupled because x1 and x2 appear in both equations. Therefore, they have to be solved at the same time. As an alternative, we can consider the following system. The 2 equations of motion for this system are given as shown here. So mx1 double dot plus kx1 equals 0, and mx2 double dot plus kx2 equals 0. These equations are uncoupled, and we can solve for x1 and x2 independently. So the solutions can be found immediately as shown here, where P1 is equal to the square root of k over m, and P2 is also equal to the square root of k over m. It's important to note that in this instance, P1 is equal to P2 because of the parameters we chose. This is not a general result of uncoupled systems. It is obviously much easier to solve for the uncoupled systems, however, and the greater the degrees of freedom, the easier the uncoupled response is compared to the coupled system. For multiple degree of freedom systems, it is always preferable to deal with uncoupled equations if possible. Now, in matrix form, these equations become this shown here. So this is again our coupled system, and this was our uncoupled system. So you can see that uncoupled equations correspond to diagonal matrices, where both the mass and stiffness matrices must be diagonal. If there are any off-diagonal terms, the equations are coupled. So you can see that in our uncoupled system, both the mass matrix and the stiffness matrix are diagonal because we have zeros on the off-diagonal terms. Now in 8.23, the stiffness terms are off-diagonal, so we have what's called static coupling. So here in the stiffness matrix is not diagonal. If the mass matrix had terms that were off-diagonal, we would have what's called inertia coupling. Both kinds of coupling can be present in any given system. Now let's look at our system again and look at our equations of motion. Now let's consider the sum and the difference of these equations. So A plus B gives us this expression here, and A minus B gives us this expression here. So we can simplify these, as you can see. So A plus B gives us m times x2 double dot plus x1 double dot plus k times x2 plus x1. So let's call this C, and then A minus B gives us this expression. So m times x2 double dot minus x1 double dot plus k plus 2kc times x2 minus x1. And let's call this D. Now we can define new coordinates z1 and z2 such that z1 is equal to x2 plus x1 and z2 is equal to x2 minus x1. Now our equations C and D become these equations shown here. And you can see that these are uncoupled. So now in equation C star, I only have Z1 appearing, and equation D star, I only have Z2 appearing. So I can write down the solutions directly, as we can see here. Where here P1 is equal to the square root of k over m, and P2 is equal to the square root of k plus 2kc over m. Now A hat, B hat, C hat, and D hat are arbitrary constants. We can note that we got the same natural frequencies using this representation. When we compare this to the system, the same system that we considered using coupled coordinates that we looked at in the previous video. Now, x1 of t and x2 of t can be found by relating them to z1 of t and z2 of t, as we can see here. So we can then, of course, relate the responses and find the response of x1 of t and x2 of t. And we can rearrange this or simplify this in terms of A, B, C, and D, where the relationship between A and A hat, B and B hat, etc. is given as shown here. So these equations can be written equivalently in this form. And this is exactly the same solution that we found in equation 8.15 in the previous section, where in that case we had the coupled equations, we found our natural frequencies from the characteristic equation, and then we found our mode shapes, which were 1, 1, and 1 minus 1. But here with the uncoupled equations, we were able to find the equivalent solution much more directly. So the main difference here is that we have found the solution using uncoupled coordinates, or uncoupled equations, in terms of these coordinates that we've called x2 plus x1 and x2 minus x1. So coupling is not a system property, but it is a consequence of the coordinate system chosen to describe the system, which is a very important concept, or a very important idea. Now let's look at the relationship to our mode shapes. So it is almost always possible to find a coordinate system that uncouples our equations. Mode shapes essentially represent the linear combinations of those chosen coordinates that will uncouple the equations of motion. So if we look at the mode shapes that we found for this system, 1, 1 represents our coordinate x2 plus x1, and 1 minus 1 represents our coordinate x2 minus x1. This was our first mode, and this was our second mode. So in this case, we were able to guess the uncoupled coordinate system, but this is not feasible in general. Generally, we have to follow the procedure that we outlined earlier. But this idea that we can find a coordinate system that uncouples our equations really forms the basis of, is the central idea of the approach called modal analysis.